All right, so what if a vector field F is defined, as you can see here, on surface S, right? Then what happens is, again, imagine F as a flow of a fluid coming out from the bottom of the surface to the top of the surface S. And we want to find out how much of the stuff is flowing across S. And remember, at each point, we have to find not just the length of F, but the normal component, because that's the direction where things are, penetrating through S, right? And so you take the normal component. Remember the normal component of um, of the vector field F is F dot n, because it's basically the norm of F times the norm of n times the cosine of theta, which is of course the dot product. Okay, remember the dot product is very useful and very easy to calculate. So this is, of course, this is a real valued function. Okay, so what we have is at every point xyz of surface S, you have a real valued function, just happens to be called f dot n. And if you integrate all that at every single point, you should get the flux, the amount of the fluid or the energy coming across the surface S. That is the surface, the flux surface, the flux integral. And that is a double integral over this parametrized surface S of, on what are you integrating? Sorry. What you're integrating is this real valued function f dot n, and then you put ds in it, right? So this has to be the definition of the flux integral. So if you are asked to calculate the flux integral, this is what you're calculating. It is basically the surface integral where the real valued function you are integrating is this normal component of the vector field f, which is basically f dot n, right? And it turns out, and this is the fascinating part of it, it turns out this is actually going to be easier than what we did here, because here we had to find RU cross RV and then find the norm of this, right? This norm, the magnitude, was easy in our example, but it doesn't have to be. This could be very complicated. It could be the square root of something that involves an expression of U and V, okay? Well, let's see what happens with this. So I say, but wait, okay, something exciting is about to happen. All right. So the question is, remember what n was? What's n? How did you find n? Well, n was, so remember you have the surface S, and then if you try to find the tangent, the plane tangent to this surface S, that was um, RU cross RV, and that will give you something perpendicular, right? Now, this one we called N. Um, yeah, that is that. All right, so this is fine. The only problem is that is not the capital N, because for capital N, we decided that we need something that's unit. Okay, so what you found here, if you do RU cross RV, that will give you something perpendicular to the surface S, or perpendicular to the tangent plane to surface S at that point. But it's not unit. It's not a unit vector. So we have to divide this by the um, magnitude of this, right, to normalize this. Okay. And by the way, I'm not concerned. Technically, capital N was used to describe the inward pointing one. That is the principal unit normal vector. Right now, I'm using this letter loosely to say, just a principal, unit normal vector. It could it could be um, it could be outwardly pointing. I don't know, but that's okay in this case, right? So capital N is found in this way. You take RU cross RV and divide by its norm. All right, now watch what happens. Then the flux integral, oh, this is exciting, okay, which is a double integral of the real valued function, which is called f dot n of ds, right? This can be written as f dot, and what is n? It's RU cross RV divided by the norm of RU cross RV. All right, and then this part here, ds. What was ds? ds was RU, the norm of RU cross RV, and then dA, right? And watch, yeah, this and this cancel each other. And so that's why I said the flux integral turns out to be often easier to calculate. This can be written as f dot, I have to be careful here. Since I wrote this in dA, this is no longer over S anymore. Remember, if you put dA, this has to be changed to D. That's the domain, in the UV plane. Okay, so this can be written as F dot RU cross RV. This is your normal vector, not necessarily the unit vector, but that unit part cancels out, or the normalization part cancels out. And so this is dA. It's basically not surprising. You may have expected this, just like this. And so let me recall, I want you to recall what we did before, okay? When we were trying to find out the work integral over a curve, right? So you have this curve, and then the work integral over the curve was C. And then remember, to find the work or the flow or the circulation, what we had to do was to find the tangential component of it, right? So the tangential component was F dot T, and the tangential component of the vector field F, which is, the real value function F dot T, was the integrand, and you integrate this real valued function over the curve C, right? But the way we did this is we had a bunch of other ways to write this, if you remember. This is F dot, okay? And how did you find R? How did you find the unit tangent vector? That was R prime, and you have to normalize it, right? And then ds happens to be the magnitude of R prime dt, right? And here you have to go A and B. And then you notice here, this will cancel. And so we saw this before, very much like what we're experiencing right now with a parametrized surface. And then this we wrote as F dot R prime dt. Remember that? And we went even further. We said, let's call this R prime dt what? dr, with a vector notation over the R. Okay. And that's where the phrase FDR comes from. And I jokingly said, yeah, FDR is always associated with work, right? As in the New Deal back in the 1920s and 30s. So so this is what happened. Things canceled with the norm of a vector. And that's exactly what we are seeing here. These two norms cancel each other. So now we're going to give this a name, okay? Just like we did with the dr. So the flux integral is the double integral over the domain in the UV plane of F dot, okay, and this whole thing is going to be called ds with a bar, right? The book is actually uses this notation where this S is in bold, and sometimes they mix this up with the regular ds. Now, remember, the ds, we had ds here, okay, and that ds it's exactly this. Okay. And so this ds is different from ds with an arrow on top of it, because that is RU cross RV. So we're not going to make a big deal out of it. What's the difference between the single S, as a simple S, and the bold S. Okay. But if you see FDS written this way, remember, this just means that the flux integral, right? So this is sometimes referred to the flux integral, but it really is basically that. It's a double integral on the surface integral of the real valued function f dot n. But from now on, because of the cancellation that happens here, we are going to use this, and you'll see this in a moment. I'll do several examples. This is what you use to find the flux integral. All right. So what do you have to do? After you parameterize the surface, you find RU, you find RV, you take the cross product, okay, and then you don't even have to find the norm of this, okay? You just dot it with F written in terms of U and V, and that's what you integrate over the UV plane over that domain, which is on UV plane. Okay, domain D. All right, let's do an example. Okay, hopefully, this is cool. Okay. All right, let's try this. I have this vector field F, which is negative y, z. negative x, z. Okay, the surface S is a vertical wall or curtain, which can be described by v square u, where u goes from 0 to 10. V goes from 0 to 1. Okay, let's try to, maybe you can stop this at this point and then try to visualize this surface S. What kind of a membrane or film or filter is this, and how is it located? How is it oriented in the three-dimensional space, R3, right? Try to figure this out. Okay, so you notice here, z is sort of independent. U is independently just z. So u will just go from 0 to 10. It'll be some sort of a cylinder, a vertical cylinder, right? Definitely not circular. And then here, you notice here that x square is v square, which is y. Right? So y is equal to x square. If you graph this, you will get something like this. Obviously it's a parabola, right? Y is equal to x squared on the xy plane. So this is what that looks like. And then u, which is z, goes from 0 to 10. So you just make this into a height of 10, and it's a cylinder. However, v, which is your x coordinate, is restricted from 0 to 1. So all we are getting is actually just this part, So this is the point 1, 1, 0. Okay, and this of course is the origin. And then you just drag this up to the top, and 10 units up here, and you get this. Right. So this is a sort of like a part of a parabolic curtain, and this is what you're seeing here. It's parabola, right? And z is equal to 10 over here. And so you can imagine a parabola and then just make it, 10 inches high or something if it's in inches. Okay, that's what this looks like. All right, so the question here is, F is giving you a vector field that describes the flow of a fluid or an energy or something. And we are trying to figure out how much of the stuff is coming across the surface S, right? Defined by the flow, defined by the vector field F. All right, so what do you have to do? The parameterization is already given, and so you basically have to follow this, right? Remember, I said your hand will probably automatically start moving at this point. You find RU, which is 0, 0, 1. RV is 1, 2V, 0. RU cross RV is, let's see, the first one will give you negative 2V, the second one will give you 1, and the third one will be 0. Okay. Now, at this point, you may want to do this, and I haven't talked about this much at all, okay? But remember I said the flux, how much is the stuff is flowing. The thing is, though, at this point, I don't even know which way it's flowing. Is the thing flowing from here to here or from here to here, right? And that sort of depends. It depends on the orientation, which comes from your parameterization of the surface S, right? And so once you find RU cross RV, remember this is your normal vector, right? And so it helps to figure out which direction this normal vector is going, because that is the direction which we are using to calculate the flow or the flux, right? So imagine here, at any point, like for instance, when V is equal to 0, if V is equal to 0, the point is 0, 0, U, right? And at that point, so let's say if U is equal to 0, we're talking about like this point here. At that point, yeah, V is equal to 0 doesn't, well, no, it does. Okay, so if V is equal to 0, the point that I'm at is 0, 0, U, okay, where U is going up and down. At any point, and anyway, this thing here, the normal vector at this point is negative 2V, which is 0, and then 1, 0, right? So if you pick the origin, which is when U is also equal to 0, this vector is 0, 1, 0. It's going in this direction. Okay, so you can tell this is the thing that moves from this side to this side. Okay, this is the direction pointing at this, right? And I think you can tell, I mean, at this point here, where, what is that? Where V is 1 and U is equal to 0, okay? And at that point, if UV is equal to 0, 1, then my normal vector is going to be negative 2, 1, 0. And negative 2, 1, 0 would be like this, okay? And so again, this is, you're going from this side to the other side. That is the direction defined by this normal vector n, which is RU cross RV. Okay, so now we know that I'm about to find the flux of the fluid going from this side to that side, okay, of the curtain or of this filter or whatever it is. All right, so now I have RU cross RV. Remember, what I need is these components here. I have to have F and I have to have RU cross RV. F, of course, has to be written in terms of U and V. So this is negative Y, Z, negative X, Z. I have to translate this in terms of U and V because we are no longer allowed to use X, Y, or Z. Okay, so what is, well, what's Y? Well, Y is V squared. What's Z? That's U, okay? And what's negative X? Negative X is negative of that, negative V, right? Z, again, is U. So you just, just convert all of these X, Y, Z into U and X. Again, this is X, this is Y, this is Z. So that conversion or translation should be pretty easy. Okay, so the flux, remember, it's a double integral. Here, let's go ahead and write down the definition of the flux. The flux is the surface integral of f dot n ds. Okay, technically that's what it is, but now we know how to calculate this. It is f dot ru cross rv dA, right? And so now we are ready to write this down. And in fact, well, okay, that's fine. Let's say my U goes from 0 to 10, my V goes from 0 to 1, right? And now I have to take the dot product, right? Let's see, negative U, negative V squared here. Let me go ahead and write this backwards. So it's negative U V squared, negative V U, dotted with negative 2V 1, 0. And so this is, this is my F dot RU cross RV, and then dV du. What I normally do is go ahead and calculate this dot product first before I even put the integral sign, but that's okay. So what is the dot product here? It's positive 2 U square V cubed minus V and plus 0. Okay, so this is my the integral. Okay, so if you integrate with respect to V first, this will be 1/2 U square V fourth, right? Because 3 becomes 4, of course. And then V becomes 1/2 V squared. You integrate V from 0 to 1, you still have U left in there. So there is non-trivial integration that has to be done here. But as V goes from 0 to 1, right, so this becomes 1/2 U squared minus 1/2. And this is what we have to integrate. So this becomes 1/4. Well, let's see. And of course, I when I try to do things fast, I make a mistake. You probably caught me a few minutes ago saying the dot product is this. It's actually not that, because you have negative UV square times negative 2V square. So there is no 2 here, right? It's 2 times UV cubed minus V. I should have known that. So that goes away. I don't erase this because I want you to know where I made a mistake. And this is a good practice for you too. When you make a mistake, you may not want to erase it, because then you have just erased um, the mistake that you have made. Sometimes it's good to keep the record of your mistakes, right? So and to just clarify, hey, look, I had a 2 here but no longer there, right? And so there shouldn't be a 2 here. All right, so when you integrate and plug in 1 and 0 for v, you get 1/2 u minus 1/2. Okay, and that is the correct integral at this point. So this becomes 1/4 u square, right? And I automatically try to differentiate this to make sure I have 1/2 u, which I do, and then you have 1/2 u, and then going from 0 to 10. So this becomes 100 over 4, that's 25, minus 5, and the answer is 20. All right, remember the flux is going from here to here. All right, so what we have just discovered is that over this surface S, from this side to the other side, the flux or the amount of flow of this object is 20, whatever the unit is. Maybe it's 20 gallons, maybe it's 20 liters, maybe it's 20 whatever, okay? But the flux is calculated as 20. Okay, so this concludes the third part of the lecture on 6.6. I want to give you additional exercises because you are assigned like 10 or so exercises. And I know that I have talked about lots of examples, but I want to give you a couple more examples. So that will be in the next section of this video.